talk about the loss of criteria and the ignition threshold factor. Talk about the current status of the National Ignition Campaign or the Inertial Confinement Fusion Campaign on the Lawrence Livermore National Laboratory. Progress since the Science of Ignition workshop, which was held last May, and new results we've taken from the Vulcan Laser Facility in some assistance with that, and then a summary. So why do we want to do inertial fusion energy? Well, obviously, you have the two reasons, really, the security of supply and the creation of a carbon-free economy. You remember 3 years ago when there was a dispute between Ukraine and Russia suddenly decided they were going to turn off the gas tap, and everyone in Germany had three very cold weeks, I believe. And I'm wondering if we actually want to have all of our energy supply being determined by foreign powers and being at the mercy of disputes between other countries. Of course, the other major reason we want to study this is because we want to create a carbon-free economy. They got the issue of climate change and global warming, and we really want to tackle this and address this as soon as we can. And of course, really, the energy sector is enormously important. It's $1 trillion industry, and if we have fusion energy, if we develop the fusion energy, then the intellectual property associated with it is likely to be developed at the early stages, and we don't want British companies and British industry to be left behind if and when we get ignition and fusion energy is developed. And there are other applications, of course. The diode pump solid-state lasers, which are being developed at the moment for the Extreme Light Infrastructure project in the European Union, they can be scaled to inertial fusion energy lasers, and they have a wide range of industrial applications. And it has the potential to revolutionize both high-energy density physics and neutron scattering science. And just to show you an aerial picture of the Rutherford Appleton Laboratory, and here you see the ISIS neutron spallation source, which you see here. Neutron scattering science was first developed by Clifford Shull, and he won the Nobel Prize in 1994 for neutron scattering science. And he basically developed it just after the Second World War as a consequence of the Manhattan Project and actually using the large number of neutrons being generated for peaceful purposes. And so you know that neutron scattering science now encompasses a wide range of different sciences in nature. And so if you start off from the hard areas, down here you have condensed matter going through to chemistry, going through to biology. And the progress has been very significant. Every year we've had increases in instrumentation, increases in detectors, and they've continued to allow a wide range of new science applications to be developed, both in fundamental science and also in engineering. And you can download, if you want to go onto the ISIS website, there's a very large number of case impact studies from the neutron spallation source and from the International Linear ILL in Europe. And these case studies, they give a very basic introduction to the impact on modern life, on energy, environment, climate, medicine, and so on. But the thing is that although there's been the increases in these neutron scattering detectors and instruments, the actual increase in source brightness of neutron spallation has actually only increased by a factor of 6 since the 1940s, when they were actually introduced as a nuclear reactor, first ones as a nuclear reactor. And so we were thinking about 6 years ago, well, how do we actually get a revolution in neutron scattering science? And we came up with the idea that you could actually use inertial fusion energy as a route to getting a much, much brighter neutron scattering science source. And so here you can see that the inertial fusion pellet, when it is ignited at high gain, will give you nearly 1,000-fold increase in the number of thermal neutrons which you can expect to see, and that therefore promises a tremendous increase and tremendous possibility in what we can do in all the natural sciences with these neutron sources. Oops, what's that? typical, isn't it? So the neutron sources are limited by two factors. Here is a neutron spallation source. So you have a proton beam, it comes into a tungsten target, and you have neutrons splating out from the nucleus, and then you have moderators capturing those neutrons, downscattering them to thermal energies. And here you have a nuclear reactor with obviously a cooling material around it with a moderator at this point. And the limitations are you have to have the heat removal from the target if you're using a neutron spallation source. If your proton beam is too energetic, then you're just basically going to heat up the material, it's going to melt, and then you have shock waves, and the whole thing is just going to disintegrate. And the last thing you really want to have is a radioactive thorium target, or tungsten target, which is just sitting in the target chamber not doing anything. And similarly with nuclear reactors, if you want to increase the source brightness, you have to go to a much larger nuclear reactors, and then you have lots of radiation damage, and of course that's rather costly. So here's the concept. You have an inertial confinement fusion target. You have an explosion of the target when it's actually fusing together, and you have a high gain. Those thermal neutrons, which are at 14 megaelectron volts, they go into a moderator. They get slowed down, and from that you can extract the thermal energy spectrum and put them into the large array of detectors which we have already illustrated, and use them for all of the scientific applications we described. And so that's quite an interesting concept. It's actually, if we can get inertial fusion energy working, we can actually revolutionize not only our supply of energy, electricity, but also can revolutionize many of the natural sciences at the moment. The other major facility at the Rutherford Appleton Laboratory, or close by to the Rutherford Appleton Lab, is the diamond light source. And we did an experiment in 2004, which published in the Nature magazine, where we, with collaboration between Imperial College, myself, UCLA, and Strathclyde, we showed that you can generate large electric fields in plasmas, 100 gigavolt per meter longitudinal electric fields, which can then accelerate electrons to very large energies. And Gear electron volt beams were first demonstrated in 2006 by Simon Hooker's group, and working in collaboration with the Lawrence Berkeley National Laboratory. And there's been a worldwide effort since then to actually optimize the source properties. And one of the things which has interested me is actually how do you actually then think about how to couple or to actually make use of these new particle accelerators. And one of the ideas is to really use, for example, a conventional accelerator like diamond, and you can then put the diamond electron beam as a driver for a plasma wave field. And if you see that electron bunch with an intense laser pulse, you can then get the bunch modulated, and that can drive a single longitudinal wave field in a secondary plasma source. So that has a large number of applications. We can create a high-energy electron beam in a second source. We can probably double the energy of the diamond beam from 3 GeV up to 6. That's the idea for doing these calculations. That actually then produces a potential X-FEL using synchrotrons, potentially using betatron oscillations with nose wakes. And potentially, you can also then do it as a proof of concept idea that you can actually generate this modulated density profile in the electron bunch and imprint it by co-propagating a proton beam with it, and imprint the proton beam, the pattern onto the proton beam. And this is extremely important for the CERN Awake project. I don't know if you've heard of this, but this is a project which has been certainly, the conceptual design report has gone to the CERN Council, and it's basically to use the SPS beam from the Large Hadron Collider, and to use that as injected into a plasma column to generate a large amplitude plasma wave, and then we're going to inject electrons to be accelerated on the back of that. And this project, we want to do a proof of concept experiment using the SPS beam, which is 450 GeV proton beam, and the idea really then is to use that beam to as an ejector for electron bunch, which we can accelerate to potentially up to 500 GeV. But that's obviously a proof of concept at the moment. But this is the calculations. This calculation was done on a 300-node supercomputer. It lasted a week. And so this calculation has been rather long in coming, but I don't really want to steal Jimmy Holloway's calculations, and he'll be giving a presentation to the John Adams Institute in the Fisher Room on next Friday. So I would urge you all to come along to that, because it's an extremely interesting set of calculations that this guy's done. He's a brilliant student from University College London, and he's coming here to tell us all about it. Of course, the other fundamental reason why we want to do inertial fusion science is because of the really intrinsic interest in terms of basic science. And I think I'd given this quote from Eddington, who was the professor of physics at Cambridge University, who corroborated Einstein's theory of general relativity. And he basically, in his book in 1926, was saying that the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. What appliance can pierce through the outer layers of a star and test the conditions therein? And that is really exciting as far as I can see. We've actually got to be able to create these conditions, diagnose them, interrogate them, and actually understand what's going on. And so here is the picture of the National Ignition Facility. You can see here the building itself is huge. And if ever you go out to California and San Francisco Bay Area, I urge you to go and see this facility. It's absolutely marvelous. It is one of the 7 wonders of the modern world. You see here that the laser bay, which is absolutely gigantic, and here is the target chamber. There's a guy in there just about at that point, and here is the outside of the target chamber. It needs to be that big because when you have an explosion of 10 or 20 megajoules, as we're expecting eventually, that is equivalent to about 600 grams of TNT, which is about the same as a hand grenade. Most of that energy is going to come out as neutrons, but some of it is going to come out in plasma. So you don't want to have the plasma diagnostics, which are going to be too damaged by it. So this target chamber needs to be pretty large. So the National Ignition Facility was completed in 2009. The ignition campaign started in 2010. And within 2 years, they had got fusion yields which were a factor of 6 of the alpha particle self-heating regime. And that's pretty exciting, as I'll show you. So here's another cartoon, which I like to show you, everybody. Why have I put this up? This is just think about how a laser-produced plasma actually how a laser pulse actually generates a plasma. Right at the very foot of the pulse, when it's at 10 to the 8 or 10 to the 9 watts per square centimeter, the electric field penetrates into the skin layer. And the skin layer, you've actually got an electric field which is oscillating, and that electric field is drawing resistance within the skin layer, and it's heating the material up. So you have a transition from the solid state to liquid, and then into the vapor. This isn't a picture, by the way, to remind you of the awful winter we just had. This is just to illustrate that when the laser pulse hits the target at the very beginning, you have an electric field of 27 million volts per meter. It immediately heats the material up, starts to vaporize, and then as soon as it starts to ionize by multiphotonization or collision ionization, then you basically get a cascade, and you get a very dense hot plasma being formed instantly. And of course, at 10 to the 9 watts per square centimeter, that's very foot to the laser pulse. It very rapidly rises to 10 to the 14 or 10 to the 15 watts per square centimeter. At 10 to the 15 watts per square centimeter, you've got an electric field of 27 billion volts per centimeter. And you have a pressure which is about 100 million atmospheres. And of course, when you have such pressures, you have what's known as a rocket effect. That you actually, if you symmetrically irradiate the outside of a shell, it's going to start off it's going to ablate off very rapidly, and momentum conservation, it means that the shell is going to implode at high velocity. In the same way, as you have with this rocket, you have the exhaust gases escaping the bottom of the rocket and imparting momentum for the rocket to escape the Earth's gravitational field. And so the velocity, the shell velocity, is proportional to the ablation rate, by the ablation pressure by the mass ablation rate, and it's just a simple rocket equation. So this is an illustration of how a structure of a laser-produced plasma. You have the laser pulse coming in to a critical density surface, which is usually around 10, for the third harmonic laser pulse is around 10 to 22 electrons per cubic centimeter. That material, which I said is heated up to very high temperatures of around 2 to 3 kiloelectron volts. At the critical density surface, the laser energy is either absorbed or reflected. And at that point, you have this very hot, dense plasma, which is starting to stream outwards at high velocity, but then it's extremely hot. And so the electrons will actually start to flow into the solid surface. And then generate a high ablation velocity at this ablation front. They'll also, because the high pressure will actually drive a shock wave through the material, and understanding how matter behaves under these conditions of extreme pressures is actually one of the key aspects of inertial fusion science research. But anyway, this material is starting to explode and implode at high velocity. The implosion velocity for the inertial confinement fusion targets in the National Ignition Facility is around 360 kilometers per second. And this is an illustration of the National Ignition Facility target. So the laser beams are irradiating the inside of a shell. You have the laser pulses, which are generated on the inner beams. They come and hit the whole round target close to the center. And on the outer cones, they impact at some more oblique angle. And this creates a uniform radiation field of around 300 electron volts. The material, the ablated material, which you saw previously on the last slide, this ablated material, you don't actually want it to fill up the cavity, the whole of the whole round material. So what happens is that there's actually a gas fill in here, and that prevents the material being ablated and filling the whole ram itself. So you're having basically a black body radiation field, which is around 300 electron volts, and that radiation field impinges into the shell of material, which is basically, you see here, is a plastic shell with deuterium ice, which is cryogenically frozen onto the inner surface. It's about 2 millimeters in diameter, the shell, and this whole ram is about 9.4 millimeters in this dimension and about 4 millimeters in this dimension. And there's an entrance hole, which you see here, which also has a plastic window, which is ablated very quickly early on in the laser pulse. So this is an illustration of the National Ignition Facility target. And one of the things which is really a problem for inertial confinement fusion is the Rayleigh-Taylor hydrodynamic instability. If you have a laser pulse coming from the top down to the bottom, you have basically light fluid being accelerating a dense fluid, and it's Rayleigh-Taylor unstable. And this is illustrated by this cartoon here, which is taken from the Los Alamos National Laboratory. And you see here the development and mixing of the shell of the light fluid into the heavy fluid. And radiation drive is actually the high ablation rate, low exhaust velocity implosions, and they're much less susceptible to this Rayleigh-Taylor instability than directly irradiating the outer surface of the shell. And that's why the Lawrence Livermore National Laboratory have actually gone for indirect drive as the main method for producing this fusion energy. So what is the function of the imploding shell? Well, what you want to do is to generate a kinetic energy which is converted thermal energy into a hotspot. So you see here the material is heated to between 5 and 10 kiloelectron volts. You have cold material surrounding it, which is at a density of between 500 and 1,000 grams per cc. And this gives an illustration of the density profile. So the shell is actually quite thin, but it's really, really dense. And you have a temperature profile which looks like this. But this is all in pressure equilibrium. What we find, though, is that half the kinetic energy of the shell goes into the low density part of the hotspot, and 50% goes into this shell material here. So the target gain is not a physics parameter. This is, you say, well, we haven't actually got gain yet from the National Ignition Facility, but it's not really something which is important in terms of the physics of actually how the thing is going to ignite and fuse together eventually. Although, of course, it's quite important when you're thinking about doing this for fusion energy applications. And I've taken this from the Life fusion reactor, which is being developed at the Lawrence Livermore National Lab at the moment. What is important is the fusion Q, which is basically a definition of the amount of energy which is being self-heated in this hotspot compared with the thermonuclear energy out. So this is the definition for thermal Q. And so the Q alpha, which is the energy of the alpha particle by the thermal input, is always Q divided by 5. So this is the definition, really, that when you have a Q of 5 or Q alpha of 1, you're actually in the alpha particle bootstrap heating regime. That is, the alpha particles are starting to stop within the hotspot itself and actually start to self-heat the material. And when you're in Q alpha of 2, which is not very much larger than that, you can then get into the burning plasma regime. That is, the alpha particles which are generated in that hotspot are propagating, slow down in the dense fuel outside it and start to propagate there. So I think that really one of the interesting things about the inertial confinement fusion concept is that you've put 2 megajoules of laser energy into this target, and only about 1% is actually used for generating the fusion energy. And the vast majority of it is actually given off as used both to heat and accelerate the blow-off plasma. And I think that's quite important to remember. That actually when you get a megajoule drive, for example, with a National Ignition Facility, you also have about 10 kilojoules, which is total kinetic energy of the fuel, with about 1% energy transfer. So that's telling you something interesting. That really you have an ultra-high amplification of this 1% of the energy which you've converted from kinetic energy into thermal energy. So you start off the ignition in the central hotspot. It then starts to propagate through the dense fuel, and then the fuel starts to disassemble at some. That's when the inertial confinement is actually finished. And for 10 megajoules of fusion yield, you have a Q alpha of about 400. And I think I wanted to put here the relationships between the target gain and Q alpha. So Q alpha of 1 is when you enter in the alpha particle heating regime, and that gives you around 10 to the 16 neutrons for the National Ignition Facility conditions. And when the gain is 0.05, Q alpha is 2, you're starting to enter the burning plasma regime. It gives you 2 10 to the 16 neutrons. A very small difference between alpha particle self-heating and entering the burning regime. And ignition is when you have a Q alpha of 20, which is, again, not very much different from those conditions. So you can see a whole stage of conditions for getting the inertial fusion target to actually propagate and introduce it and to release its energy. So with magnetic confinement fusion, of course, we know that this is the Lawson criteria, which is important. The pressure times the confinement time has got to be greater than that for ignition, greater than 1. But you can write it as an alternative form, where you have the Lawson criteria is proportional to the compressed areal density of the fuel, the neutron yield when you don't actually include alpha particle heating, and just the mass of the fusion fuel. And what we find is that the ignition threshold factor, which is the definition for fusion energy gain, is basically proportional to twice the Lawson criteria. And what we find is that experimentally we've got a Lawson criteria of about 0.2, and if you just take the ignition threshold factor, we're about 0.3. So it's very, very close. That's the remarkable thing about the National Ignition Facility right now. I've taken this slide from Riccardo Betti, who's a professor at the University of Rochester, and you can see here the fusion, the Lawson criteria for JET and for Omega laser, which is 2009. And the National Ignition Facility, as of the present moment, is around this point. And we're expecting to move up into this regime in the future, and we should be entering the ignition regime at that point. But this is the regime which we are at the moment. And I wanted to show it to you because you can see also the JET facility, which is down the road at Culham, and this is also at this point. So they're quite close together. That's the important point that I'm trying to get across to you. So at the moment, the neutron yield is around 10 to the 15 from the measurements. That corresponds to about 2.8 kilojoules, and it gives a Q of about 1.2. And remember that a Q of 5, which is proportional to Q alpha 1, entering the alpha particle heating regime, is when you have a Q of 1. That's when you have a Lawson criteria of about 0.5. And ignition obviously is when you have Lawson criteria closer to 1. But that means that we're only within a factor of 5 or 6 of the neutron yield needed to access the alpha particle bootstrap heating regime. So in terms of this ignition threshold factor, which is being developed in the Lawrence Livermore lab, you have the implosion velocity, the shape of the hotspot, the mix of the fuel, and the adiabat. And these are the 4 campaigns in which the National Ignition Facility has broken up the campaign in terms of looking at the physics of this of physics of ignition. And so if we look at velocity to start with, you need to first of all get the radiation temperature to about 300 electron volts. If you go too far below 280 electron volts, then you can't drive the thing sufficiently fast. You can't impart sufficient kinetic energy for it to, when it actually stagnates at the center of the implosion, you can't convert enough of that kinetic energy into thermal energy, and you can't ignite it. So you need a radiation temperature of around 300 electron volts, and this is showing you that with a uranium foil, with uranium coating on the inside of the whole RAM, they've actually managed to get to 300 electron volts quite dramatically. This diagram on the right is showing you the absorption fraction of the total energy being absorbed into the whole RAM. And this is showing you that for an incident laser energy of 1.7 megajoules, they're getting 85% energy transfer into the whole RAM, which means that it's quite dramatic, the absorption of the laser energy field into the whole RAM. So here's the velocity. Continuing with the velocity, you're basically looking at radiating a zinc foil, which is then imaged onto a slit of an X-ray street camera. So you're basically taking a one-dimensional image of this target, and you're doing it in time. And so you have a one-dimensional space in this dimension and time in this dimension. And you see the shell is starting to implode at very high velocity and starting to see self-emission at this point. And so you can actually get the implosion velocity to be fairly well accurately modeled. And they've changed materials. Obviously, with a 300 electron volt radiation field, you don't want the harder X-rays to penetrate through to the cryogenic or compressed fuel, which you're trying to compress to high density. So what they've changed is the layer which they're using to stop that X-ray preheat going from germanium to silicon, and they found quite a dramatic increase in the implosion velocity as a result of doing that change. So in terms of the other aspect of the ignition threshold factor, the shape of the whole RAM, what they found is, the National Ignition Facility, is that you can actually transfer energy from one cone of beams to the other, so you can compensate some of the energy losses on the outer cone, on the inner cones of beams, which are hitting at this point. You can transfer energy via a diffraction grating, which is set up by a plasma instability at the entrance hole, and you can transfer energy quite efficiently according to the wavelength separation which you can introduce into the laser itself, and the density, the saturation of the plasma wave which has been generated. And you can actually quite nicely see the hotspot shape changing as you change the wavelength separation of this wavelength separation, which actually then is transferring energy from the inner cone of beams to the outer cone of beams and symmetrizing the radiation field and giving you a nicer symmetric, more symmetric implosion. So this is the other aspect of it, that you want to make sure you're not preheating the fuel too greatly. And what they found is that if you change the shape of the final push of the laser pulse from being a square pulse to being one which has a 3 nanosecond rise time, it actually produces a colder and denser fuel at the timing of the fourth shock. And that means that they can actually now get the aerial densities required for the ignition itself. So the aerial density is just a measure of the amount of fuel mass compared with the radius. So this is the final aspect of the National Ignition Campaign, and that's the mix. This is the Rayleigh-Taylor instability, which I showed you earlier. So you're trying to mix, or prevent a mix of the outer plastic shell material into the inner shell, inner region of the implosion. Why do you want to do that? Well, if you have too much high Z material going into the central hotspot, you basically have more bremsstrahlung radiation losses than you have alpha particle self-heating, then you don't get ignition conditions occurring. And what they found is that with thinning the ablator, the thickness of the plastic shell, they can actually show that you can transition from high mixed regions to less mixed regions. So this is a cartoon of where they've actually got to. They started off in September of 2010. They then started the ignition campaign, and then they've basically increased the ignition campaign to reach around aerial densities of around 1.5 grams per square centimeter, which is enough for getting fusion ignition to occur, but not the temperature which you need in the hotspot. So this is the issue at the moment. If they try to drive the thing too hard, they find that the obvious thing to do is to try and go up this direction towards the alpha particle self-heating regime. When they try to increase the implosion velocity, they find that the neutron yield is going down here, or the compressed density is going down here. So they're basically mixing material. So you're driving it too hard, you're becoming more Rayleigh-Taylor unstable. So we were looking at this. I sent a student postdoc out to Lawrence Livermore Lab to try and help with the National Ignition Campaign, and we found a very interesting effect that this process which you saw earlier about the shape, about this cross-beam energy transfer, this actually, if you just rely upon the self-emission of the target, you find that the self-emission can be quite deceiving. This is a calculation of the fuel compressed aerial density when you impose what's known as a P4 asymmetry on the capsule implosion. And it looks quite nice in terms of the self-emission. But when you actually look at the real shape of the fuel, which you see here, more than half of the energy is still not converted from kinetic energy to thermal energy. You're finding energy is still, mass is still moving around inside the target as a result of this non-symmetric drive. So John Edwards, he's the Associate Program Director for Inertial Fiber Fusion and High Density Science. He came here to Oxford last week, and he gave an update on the most recent results. And he's found that you can try and correct for this P4 asymmetry, which we identified, or I should say Robbie Scott helped to identify. And that time-dependent asymmetry is associated with the fact that you have potentially this cross-beam energy transfer mechanism may be time-dependent. And there are other laser plasma if instability effects as the laser beams propagate through the whole RAM gas. And that's quite interesting, that there's still some unknown physics here about how this time-dependent asymmetry is developing. He also found that they've shot some higher radiowatt targets, and they found that with X-ray radiography, they can see an imprint of how the shell material, how the shell holder is actually imprinting itself on the capsule as it's imploding. And they found that with higher adiabat implosions, they can actually reproduce the implosion performance with to 70% of their calculated implosion characteristics. And also this tent effect, this imprint of the holder, actually goes away. So that's quite encouraging and quite exciting. And obviously there are many other aspects of the ignition campaign which still requires a lot of further investigations, and I think this is one of the reasons that OxCHEDS, isn't it? OxCHEDS has been formed at the University of Oxford. We're going to be looking at most of these issues of high-density material properties, and how those shock waves, which I showed you at the beginning, how those propagate through the material, how they affect the adiabat, the heat, preheat, and all that. Then you have the implosion hydrodynamic and shock waves, the parametric instabilities, and the X-ray generation, and the stagnation properties and the burn, because those are still unknown properties at the moment. And I think one of the key features about the progress which has been made by John Edwards is that he showed that they had used this, they had corrected the gross P4 asymmetry by using X-ray radiography, but it was rather a poor radiographic technique. They were only able to measure the shape of the compressed fuel only out to about one quarter of the way into the implosion. Of course, you've got to go down quite a lot, substantially lot further than that. We found in the calculations we did of the P4 asymmetry is that the gross, when you get out to those sort of diameters or radii, you find that those P4 asymmetries are pretty small. But when you actually get to the compressed densities, which you need for the ignition part of the fuel, then those asymmetries become pretty gross. And so what you need to have is a much more precise method of radiographing these implosions and actually getting a look of actually what the real shape of the fuel is, not what the shape of the hotspot. And this is the NIF arc radiography capability, which has just been implemented at the Lawrence Livermore lab. It's going to take 10 kilojoules of a quad of beams from the National Ignition Facility and convert them to short pulse to 1 omega to about 10 picosecond duration, and potentially up to around 10 to the 19 watts per square centimeter as a method of actually radiographing radiographing these implosions. And so that's interesting that you actually have this NIF arc capability, 10 kilojoules of short pulse energy. You can do a tremendous amount of science with that. And I've been very interested, obviously, in the last, as Justin mentioned, that if you actually get a gain of 10, which imagine now you have ignited the fusion target, you need to get to conditions in which the target gain is in inertial fusion energy relevant conditions, which means you need a gain of 60 or more. And you can do this in 3 ways. You can increase the burn-off fraction of the DT fuel, and that requires you to go to much larger drive energies. So if you have 2 megajoules at the moment, just scaling it up means to get to the gain of 60, you're going to need a 5 megajoule driver to do that. You can decrease the implosion velocity, and that increases the fuel mass, but then you also need to have a bigger driver, and this is the kind of trade-off which the life people are actually doing at the moment. Or you can explore alternative methods for igniting the target, and that's way we've been doing. So at the moment, what I've been talking about is a central hotspot ignition concept, where you're basically generating a hotspot in the center, and then you have cold fuel around it. But if you actually just compress the fuel to relatively low implosion velocity, to not as high density, but then you heat the material on the side of the fuel, then you can generate a hotspot at this point. And then you can actually, because you don't really care about the hotspot or the mix or anything like that, you can actually implode much more fuel mass. And of course, once you've just got this thing up to the ignition temperature, it really doesn't matter what the shape of the fuel is. It can be potato-shaped or any other shape you like, obviously within reason. But what it means is that you can get a much higher fusion energy gain if you can generate this thing by fast ignition. So there are 2 methods of doing this. The first original concept was putting forward a relatively intense laser pulse. What do I mean by that is that when you get to 10 to the 18 watts per square centimeter, the electric field of the laser pulse is sufficiently large that within one oscillation, the electrons in the oscillation of the transverse electromagnetic wave, they acquire the rest mass of the electron. And when that happens, you basically go into the relativistic regime, so you're above 10 to the 18 watts per square centimeter. And when you do the calculation for the radiation pressure, you find that the radiation pressure of the light pulse is 300 million atmospheres of pressure, which is pretty enormous. And when you get to 10 to the 21 watts per square centimeter, which is what the calculations you need, you get 300 gigabars, which is just incredible. But anyway, this radiation pressure can just push the plasma aside, and if you have a sufficiently long channeling pulse, you can then evacuate that channel for a subsequent petawatt laser pulse to come in, hit the relativistically corrected critical density surface, generate a huge current of fast electrons. Those fast electrons have the same range as the alpha particles in the hotspot, and then you basically can heat up the material before it has time to disassemble. So you can either do it by this hole boring scheme, or you can insert a cone inside a shell and make sure the cone tip is actually very, very close to where the compressed fuel is actually assembled. And we had some success initially with this concept, and we published this in Nature in 2001 and 2002. And the idea is you compress the fuel in this area, and then you inject the petawatt laser pulse, generate fast electrons which propagate into this compressed fuel and then heat it up to thermonuclear temperatures. We measured up to nearly 1 kilo electron volt, which 1 electron volt, remember, is 11,000 degrees centigrade. So 500, so nearly a kilovolt is about 10 to the 7 electron volts. 10 to the 7, 10 million degrees centigrade. So what we found doing these experiments is that this was with those measurements were done with a 500 joule laser in 2002, and people have now built even larger laser facilities in both Japan and in the United States at the University of Rochester. And they've looked at how the energy transfer mechanism actually occurs under those conditions with much more energetic laser pulses. At the University of Osaka University, they have reproduced the results which we got in 2002. So they've actually got back up to the 10 to 20% energy transfer regime. And at the University of Rochester, they found a conversion efficiency of around 4% of the fast electron beam into the hotspot energy. Now, 4% isn't that great, and you need about 20 to 30% energy transfer for fast ignition to be reasonably viable. Otherwise, you have a megajoule driver energy, which is pretty impractical. But the other factor which is found is that when you get to when you get to these relativistically high intensities, the fast electron beam doesn't actually just go in the forward direction. It just sprays out in a very large cone angle. And we found in 2008 that when you scaled this whole effect, you found that this divergence of this beam was pretty dramatic. And so that started us at the Rutherford Apton lab actually correcting for this divergence angle. And so we found you can put in two pulses to actually control this thing, or you can introduce resistivity gradients, which generates magnetic fields, which can actually those magnetic fields are sufficiently large to control the divergence of the fast electrons. And these are demonstration experiments which we published in the last last 4 or 5 years. But this experiment, which I'm going to describe now, I'm actually looking at a laser pulse, this is a direct drive compressed laser pulse. And so here's the hyper design. Basically, you have 300 to 400 grams per cc here, and then you have a coronal plasma which is being blown off by this rocket effect that I showed you earlier. And so if you inject a relatively intense laser pulse at this 10 to the 18 electrons per cubic centimeter, you find that it has to propagate around 6 millimeters in order to propagate through to the compressed fuel. But if you are at a third harmonic injection point, you have to only propagate through 2 millimeters. So what we did was to do an experiment on Vulcan where we mocked up this injection point. And so we have irradiated a plastic target, let the material stream outwards, and then we injected the laser pulse at this 10 to the 18th surface 2 millimeters away. And here's the schematic of the experiment. Pardon me. Here's the plastic target, which you see here. We were radiating this with a 400 micron diameter, 10 to the 14 watts per square centimeter second harmonic laser pulse. It's generating this blow-off plasma. And this is this calculation, which I'm showing you here, is a two-dimensional simulation using the hydrocode from the Lawrence Livermore lab, and that's just taking the central portion of it just to show you the density profile. And so we injected the laser pulse at this 2 millimeter point, and you can see the result is that you can see here that there is a laser focus, and then there's a channel being formed almost all the way through to the critical density surface. And then really at the back of the target, you can see this this fast electron beam emerging from the back of this target and forming a current loop, which is circulating around to the front. And this is kind of one of those eureka moments which you see sometimes you go into experiments and you feel that 5 weeks of really hard work is actually worth it. And so what you're seeing here is, this is the original target position here. And so what you're seeing is that the laser pulse is self-channeling and focusing the fast electron beams which are being generated. So here's a current loop simulation. This was taken a week on the Scarf Lexicon supercomputer at Rutherford Appleton Lab. So the laser pulse comes in, it generates a magnetic field. Some of those electrons escape, but the vast majority are pulled back because of charge neutrality. So you get found this fountain field which occurs on the back of the target, and that magnetic field is sufficiently large to form that current loop, which we saw there in the radiograph. And so we did a full-scale two-dimensional particle cell simulation of this effect of focusing the laser pulse 2 millimeters away from the target surface. And what you can see here is this is the kinetic energy of the fast electrons. This is the magnetic field. This is the density of the channel which is being generated, and this is the energy of the fast electrons. What you can see here is there is some evidence for the Hosing instability being occurring, but the majority of the fast electrons are generated out here in the coronal plasma, and this magnetic field is actually focusing them and forcing them not to diverge too greatly. And that's pretty nice, because it means that you can generate an fast electron beam which is only 10 degrees divergence angle. This compares with the 40 to 100 degree divergence angle we measured in previous experiments. And that means that when you have the NIF-ARC facility, which we talked about earlier, this radiographic capability, you can actually do scaled experiments to enable the tests of both this channel-formed laser pulse and also the coning shell laser pulse. And this is a really quite exciting development. So I'm going to leave you, and this is my final slide. I'm just wondering, for those of people who are also interested in magnetic confinement fusion, we've used neutral beam heating and radio frequency heating used extensively in JET and in ITER to raise the ion temperature burning plasma conditions. And we only need to raise the temperature from hotspot from 3.5 keV to 5 keV to get ignition on the National Ignition Facility. So can we use auxiliary heating? Can we use this electron beam, which we've just shown you can be generated, this narrow divergence beam? Can we induce magnetic turbulence via the two-stream instability? And if we can, then we can actually cascade the energy from the fast electron beam down into the ion population and transfer the energy. I'm putting this up as speculative idea, where we only need, as I say, 2 or 3 kilojoules of energy to heat the target. So can you use an X-ray laser to do that? I'm throwing this out there because I think it's really quite an exciting possibility. You can actually think about ideas of where you can generate really huge X-ray beams. For example, if you have 100 kilojoule drive energy onto a plasma, at the moment, Zolfur Najmuddin and Imperial College and Stefan Knipe, they've shown that when you have a laser wake-field accelerator and they undergo betatron oscillations in these channels, you can actually get quite energetic X-ray beams being generated. But why not use this self-modulated self-modulation instability to drive a X-ray beam of really enormous energy transfer? So that's one of the things I'm thinking about at the moment. And if anybody's interested in magnetic confinement and wants to help with this magnetic turbulence to induce the auxiliary heating, well, that's another possibility. So I want to summarize. I think we've made remarkable progress, and it has been amazing progress in the National Ignition Facility in the last 2 or 3 years. The ignition conditions are only within factor of 5 current neutron yield, so they're within a factor of 5 or 6 of the entry into the alpha particle self-heating regime. There are a number of physics uncertainties that remain, and with that, of course, is the timing of ignition. But I think new diagnostics hold the key to progress. And I just showed you that we have had small-scale demonstrations of the divergence issue for fast ignition. These need to be scaled up to much larger energies, of course. And I've shown you that we have narrow divergent electron beams being driven in the hole boring regime, and maybe we don't need a second petarod laser pulse to generate the fast current. Maybe there's sufficient energy. We can generate conditions under which there's sufficient energy in that initial pulse to do some interesting science. And I think I wanted to show you this last cartoon, because I'm quite keen on these cartoons, as you know. And this is just to show you that, to illustrate really that unless you have diagnostics of sufficiently robust, you just don't know what you're actually looking at. This guy here, touching the elephant's trunk, it says, well, it's a tree. And this guy here, touching its tail, well, it must be a tiger. If you don't have the diagnostics to tell you what's going on, you're really a little bit in the dark about what's really going on. So I think that new diagnostics, new techniques for interrogating these plasmas is really the key to progress. I want to acknowledge everybody again for their help in this preparation of this talk, and I want to wish everybody a wonderful spring bank holiday. Thank you.